Okay, in this lecture block I'd like to give you a very brief introduction into the area of deep learning. Why is that? Because deep learning and the successes in the visual domain of recognizing objects and also in the area of natural language processing gave rise to the idea that artificial consciousness might actually be around the corner. Several scientists over the last few years has made statements in that direction, and that is part of the motivation why we are actually dealing with that topic in the summer term. Well, the practical application, of course, is always something different. What we are going to go through briefly is, in particular, the basic notion. Oh, almost. The basic topology, the event we will manage. Then we will speak about recurrent networks. And we have to speak about risk and reward. Of course, there will be many more topics. As always, this is not a very technical lecture here in the summer term. In the winter term, if you're interested in that, you can go to the courses where we go through that in detail, compare the classic methods of artificial networks, other machine classifiers with today's notions of deep learning ones, and identify why are these three notions interesting for us. Rewards are interesting because rewards bind the neural net, the brain, to physical reality. Adaptation to the needs of the outside world has to be rewarded somehow, otherwise, at least by survival or by better adaptation, by higher motivation, in order to give the brain an incentive to actually adjust its structures. Recurrent networks are important because, as we said before in other blocks, almost everything is atemporal. Therefore, if we don't have an explanation for that, we are actually not explaining very much. Here in particular we will have a brief look at the topology that is known as the long short-term memory, because it is very intriguing and very interesting to discuss. And we have to deal with losses here versus our motivation. And the topology is, of course, important as an introductory pattern. There we will focus on the most fundamental structures, in particular convolution versus classification. These are two patterns that we already mentioned in Media and Brain 1, and we come back to that. Okay, so let's go on first with the basic topology. What can be said about that? Well, one thing is very important. We have to measure similarity in neighborhoods. That means not comparing one stimulus, something that comes along that is perceived, to everything that is in the net, but only to what is related to it, what is close by, either spatially or temporally or in some abstract sense, and that is what we know as convolution. And a convoluting neuron has a number of inputs and fires based on that. Such a neuron might be seen as, if you like, as a concept agent that deals with semantic enrichment. The most fundamental function that we have in the brain and that goes over stages and stages. So let's call this a concept agent. Convolution, as we have seen in media and brain 1, is a similarity measurement operation. It measures the similarity of the inputs with what is already stored in the cell, in its topology and its connections, the weights, the activation potential, the past knowledge of the world. And since it's only in neighborhoods, as we say here, it means that these inputs are limited in some sense, spatially, temporally, as I said. Okay, and that makes the notion highly similar to what we called in media and brain 1 and what is called in neuroscience in general a pathway. A pathway is described that the same operations in the same stages are employed and executed on groups of pixels or groups of input signals. It can be thought of as a processing chain, one step after the other. Typical examples are the pathways of the visual system, also the auditory pathway, and so on. So these are processing chains for what comes along. Very important. On the other end, we have apparently the notion that the outputs of the pathways are weighted down by a sigmoid function that is something like this. And discriminated either to +1 or to 0, meaning that some of them are considered to be relevant topics of the inputs. If here come the pathways, whereas others are considered to be irrelevant. That is a discriminatory function. It gives an exponential weight on some and it reduces the weight exponentially for others. In the event, you can pick one as a winning node, as we would say in machine learning, or as the maximum likelihood, or as the one in neural terms that is actually firing, that is actually able to relieve an action potential. And that notion is very similar to what we have in the brain as centers. So, both of these concepts are available in neural networks, for example, in so-called convolutional neural networks, which is very satisfying, of course, because we know that to a degree the structure that we use in the artificial nets is also there in the neural nets. There is a third notion that what I would like to explain here very briefly, and that is how to deal with the problem of overfitting. Overfitting means that we have certain stimuli, other we have not, but still we know that they do exist. And how do we prevent the neural network, either natural or artificial, to adopt too strongly what we already know and stay open to new stimuli that might require different conclusions? Interestingly, the standard solutions in, for example, the convolutional neural networks are forgetting. For example, with dropout layers, and of course partial learning. With the notions that we already had in the earlier videos, to learn something partially would mean that to work on an earlier concept prototype. And learn only that one, and not learn a more abstract one. So to work on lower levels of abstraction. That is in the event, for example, pairwise learning of layers as we use it in convolutional networks. Okay, that is essentially everything I wanted to say about topologies. We have equivalents for pathways in modern deep networks. We have equivalents for centers. These are not very sophisticated, by the way. The strong power in the artificial neural network certainly lies in the complexity of the pathways, and particularly in the amount of data that can be stored there, and also the introduction or the usage of measures to counter overfitting is of course very important by, for example, dropping out connections randomly or based on a more sophisticated scheme, but on the other hand also by partial learning, working on earlier prototypes, working only on part of the semantic space, as we would call it, by, for example, pairwise layer training. Okay, so that was the first part, basic topology. Next thing we are interested in is recurrent networks and the LSTM. I would like to give you a very brief introduction of how that concept actually works before we go to the question of how we can get our rewards and our risk minimization in the process in a way so that maximum effect is actually guaranteed. So, what is the idea of a recurrent network? It's very simple. In later stages of processing, if time goes here, and here we have a processing chain of complex layer structures, you might feed earlier stuff back into layer laters. If this was a Markov process, then we would say it would not be of zero order but of some higher order. What's the effect? The effect is that if we have a problematic signal here, like one that is, for example, degenerating, then we can, to a degree, refresh it from what we had in the earlier stages. Furthermore, the particularity of the semantic enrichment at this point might be enhanced by having the background knowledge from earlier stages. So there are many good reasons thinkable why doing such a recurrent processing might actually increase the signal to a degree. Such methods have become quite popular over the last few years. The major problem of them is, of course, training them, finding sufficient amount of data to do the training. One pattern that is of particular interest for the domain of language processing and therefore of semantic understanding of language is the long short-term memory. As always, again, we can only give a basic overview of what is actually happening, and I can point out that the principles is mostly about clever usage of entropy and of aggregation of information. We mention it as it is important in the area of language domain, and as it might also tell us something about how actually gates and memory patterns can be used in order to create consciousness. So, very briefly, what do we have? We have actually 5 processes in a long short-term memory. The first one being that the input is simply concatenated to what we already have. So the input and the signal are concatenated. That means if you have LSTM cells in a layered structure, then the register becomes broader with each element in the sequence. That is an interesting aspect of the individual layer. And these registers are, if you have multiple layers, also propagated to the next level. whereas the knowledge apparently lies then in the end of the sequence, both horizontally, so to speak, and vertically, though these things, of course, have no particular meaning here. Okay, the second function that we have after the concatenation and making the register broader is that we actually discriminate the concatenated signal. Discrimination is done again by employing the sigmoid function. So pushing those elements of the vector with a low value towards 0 and the others towards 1. That gives us an input that we shall call the state vector. Having that state vector, we can employ it on all the signals that we have in the LSTM. We have, of course, the signal itself, the actual information that flows through it, and we have a memory of that signal. In the first processing state of the memory processing, we forget part of it. In the second, then, we augment the memory and propagate the memory further. So what happens in the forget state? In the forget state, we simply multiply the result of the discrimination operation, the state vector, with the forget, with the memory input. If we multiply that element-wise, then of course those that were pushed towards 0 cause forgetting part of the memory, whereas the others cause maintaining part of the memory. Okay, that cleared memory is then augmented again by the input vector by summing it up with what we have in the memory and what we have on the input side, and there employing a tangent hyperbolicus function. That is very similar to the sigmoid function, only that it goes from -1 to +1. So if we do that, then apparently we are not throwing away data, because 0 is not an important spot in that function, but 0 is just somewhere in the middle. However, some inputs, depending on their values, on their variances, are pushed to the negative side, such causing the memory to wander in one direction, whatever the semantic meaning is, and others into the positive side. So they're pushing them apart actually. And that creates the memory output of the individual cell. The memory is in the event, in the last state, used to create the output, where again on the state and on the input vector and on the memory, by employing again the tangent hyperbolicus here and here, we enhance the signal that is stored in the long short-term memory cell. So, to wrap that up, what happens at this in this function? What we do is we keep a memory of the past, and we keep a signal. The context might be grammar understanding, grammar analysis, might be phoneme analysis, might be any temporal structure, might be optical flow analysis of movement in the visual field. All that would be useful or could be used with the long short-term memory. It is very important that the register gets broader with time. So here, that we employ a sigmoid function for discriminating, for forgetting part of the signal and keeping others. Employing that, multiplying that, causes the forgetting. And then the augmentation of the memory and of the input signal are both based on what we have in the register, what we had in the memory, and the tangent hyperbolicus function, which is not discriminative, yet weighting into positive and negative side, thus creating a distribution of variance to a broader spectrum. So these two functions together actually are, if you look at them closely, for which we don't have the time, are very similar to the notion of the Boltzmann theorem, that is, of the entropy formula. What the long short-term memory actually is doing it is keeping a memory of the amount of variance, of the amount of entropy that we actually have of the signal. Then the past. The more variance we had, of course, the more interesting, the more volatile the input signal apparently can be. So the more advanced also the signal can be. And we use this memory information to create the output pattern and enhance it step by step. That is the long short-term memory, very briefly, in a nutshell. Why is it relevant for us? Because, to a degree, it implements our gating mechanism. Here, when it discriminates and forgets, that acts like a gate for the input data. And because it weights various inputs, sums them up over time, it's one cell after the other, and that is very similar to the pattern that we developed for the temporals in these three elements, so that input signals are transformed onto higher levels of processing by measuring entropy, by individually weighting so that the maximum variance is used, and by guaranteeing that the sequence is also kept in order. Thus, we have a typical example that is practically applied, and very successfully so, to distinguish different forms of patterns in two ways. Discriminate the patterns that are not related, and grouping together, forming a concept of those patterns that actually are related to a degree. So that was it for the long short-term memory. Again, if you would like to hear more details, a more technical discussion of that, then of course that comes in the winter term, where all the details of the computation are executed and you see that it actually works practically beyond the conceptual level. Last thing I'd like to speak about is risk and reward. The fundamental problem of all learning in computers as in human beings is whether we learn correctly. That one doesn't work anymore. So let's work with this one. Okay, the possibility that we might not learn correctly is called a risk. And it is measured in terms of loss. Again, there is extensive theory on how actually what kind of loss functions you might have. Those influence the process of your learning. What types of risk can emerge, like overfitting in terms of a classifier that is too over-complex and too much based on the inputs that were provided in the training sessions, versus on an underfitting classifier that is not able to distinguish and discriminate the classes that we have. That is not the topic of today. The question is, how can we organize that? How can we optimize the risk? And both in natural and in artificial environments. And the solution for that is referred to as reinforcement. Reinforcement is apparently a learning procedure. Why is that relevant here? Because reinforcement actually means that Reinforcement actually means that we, at the moment, at the point in time when the learning happens, we are not able to say what the loss will actually be. Only later, based on the behavior of the subject under learning, we can recognize whether or not behavior was correct or not. And that fits very nicely with the model that we have in the brain. We have the neurons in the central nervous system that are locked in a block, in a hamburger if you like, between perception and motors. So that it's not directly observable, but only after time. And therefore it requires reinforcement. Furthermore, apparently in the brain, it's not possible to unlearn. So there is no chance for backpropagation. Without backpropagation, it means that if a pattern has been learned incorrectly, we must learn it a second time differently. Methods that help us to do that are maybe our sleep, where we aggregate patterns and form variations of existing patterns of things that we have experienced before and employ them in varied forms so that the brain maybe strengthens connections that have in the past been neglected. Other examples are neurons that are firing together, simultaneously, and there are many more. The point is, reinforcement learning means rewards are delayed, they are uncertain, and they are outside of the system. And that is precisely the situation that we have in the human brain, if we consider that example. That's why I mentioned the term. Furthermore, on the pure technical point of view, if you think of, for example, of generative adversarial networks, then there you have a typical reinforcement learning situation where one producer tries to identify the right parameterization for a certain learning problem, and the second one, the teacher, the checker, actually discriminates the different parameter sets based on their performance and the quality of the output. Okay, that's about it, what I wanted to say about risk loss on a non-technical level for all sorts of networks, in particular recurrent ones. Given the topologies that we have in modern deep learning networks, that is a brief introduction into that domain.